Hi, welcome back to Calculus. Today we're looking at section 2.6, limits involving infinity. So these are going to be limits as you go really far out towards either positive or negative infinity, and then we'll also look at limits where x approaches a number, but the limit itself is infinite. So let's get started. We're going to look at that first case first. We're going to look at what happens as you go out towards infinity. So f of x has a limit L as x approaches infinity, or you can do it with negative infinity. It's two different definitions. I wrapped them into one. And we write that the limit as x approaches infinity of f of x is equal to L if for every epsilon greater than 0, there exists m such that x greater than m implies that the absolute value of f of x minus L is less than epsilon. Now, I don't like what I had on the board, so I'm going to get rid of that. I want to draw a picture here. So let's just kind of sketch. I'm just going to sketch something that's in the first quadrant. So this is probably a graph of like 1 over x, something like that. And actually, we're going to look at 1 over x here in just a minute. So the idea is this. Just like any other limit, we want to be able to get as close to it as we possibly can. Now this one looks like as x goes out to infinity here out on the right, that this limit is probably getting very close to 0. Right, we can see that my graph is squeezing in on 0, and it seems reasonable that if it goes even further, it's going to get even closer. And so we could say here that it looks like my limit is 0. And here's what the definition says. For any epsilon we pick, so I'll call this limit plus epsilon, just like we did before. I'm going to take that limit and add the epsilon on. It just happens that this time the limit is 0. And then we would have limit minus epsilon underneath it. At some point, you get to an m, and in this case, it looks like it's right about there, where once you get past that, the function is going to be forced to be squeezed in as arbitrarily close to that limit as we want. So that's kind of the idea here. So now I'm going to take this definition, and we're going to do an example. And we're going to show that we actually have this limit that's at infinity. So hang on a second. All right, so now let's look at this example at infinity. We want to show that the limit as x goes to infinity of 1 over x is equal to 0. Now you can convince yourself of this pretty easily. Just keep throwing bigger numbers in there for x. And when you do that, 1 divided by those really big numbers gets very, very, very small. All right, but we want to do this just a little bit more rigorously. So let's let epsilon be greater than 0. We need to find an m such that if x is bigger than m, then that implies that 1 over x minus 0, the limit that we're trying to get to, is less than epsilon. Now importantly, in this case, although it doesn't matter, we do have absolute values here, but x is a positive number. We know this because we're only paying attention right now to the right-hand side of the graph as x goes out to positive infinity. All right, so let's take a look at how we're going to do this. So let's start with 1 over x being less than epsilon. That implies that x would be bigger than 1 over epsilon. And so all we're going to do is we're just going to set that equal to m. Okay, we want this to be less than epsilon. That's the same thing as just 1 over x. Again, the absolute values don't really matter here. And so I can take advantage of the fact that if I take a reciprocal, all I have to do is switch the sign. So if x is bigger than 1 over epsilon, then it looks like that's going to be what works. So to prove it, we say let m be 1 over epsilon and x be something greater than m equal to 1 over epsilon. Then the absolute value of x is greater than 1 over epsilon, because again, this was m. When we take that reciprocal, that implies then that 1 over x is less than epsilon, and we can throw the 0 in just for kicks, actually because we need it as part of our definition. And so the absolute value of 1 over x minus 0 is less than epsilon. And that is exactly our definition of having a limit at infinity. So, all right, let's move on and look. Oh, one more thing before I move on. It's worth pointing out, and this is a theorem in your book, all of the limit laws that we learned back in section 2.2, they apply even at infinity. So if you have a known limit for something at infinity, you can do all those things. You can do sums and differences and products. You can do quotients. As long as you're on 0, you can multiply things. They all work. It's a little weird, but it does work. All right, let's move on and go on to the next example that I have. Okay, so my next little example we have on the board here. The limit as x goes to negative infinity of 3 square roots of 2 over x squared. So you'll notice this there's my division by x that we just looked at. I did change it just a little bit. Now we have it going to negative infinity. But guess what? This is also going to go to 0. Because if x is negative, the same process works. If you don't believe me, go back and try that last example that we did, only send x to negative infinity. And I promise you can make it work. So we're going to use that fact, that the limit as x goes to negative infinity of 1 over x is 0. So what I did, just to kind of break it down a little bit for us here, is I said, okay, I want something that looks like 1 over x. So I broke out that limit of 1 over x squared. And I can do that because, remember, we can square things. That was one of our limit laws. So I know that the limit of 1 over x squared is still 0. And the limit of the constant that's on the top is just that constant. Long story short, it just doesn't matter. We end up right back at 0. All right, so now we're going to look at rational functions, and we're going to look at their horizontal asymptotes. Now, if you took college algebra with me, which at least 1 or 2 of you did, remember that rational functions, as you go out towards infinity, they do have these horizontal asymptotes where they level out. We're going to look at how to find those, and it's really pretty straightforward, and I think you'll be okay with it. So let's take a look. All right, for my next example, we're going to start looking at rational functions. So rational functions are functions like this one over here, f of x equals 2x squared minus 3x plus 1, all divided by 4x squared minus 2x plus 8. We'll get to this mess over here in just a second. That's a rational function. Polynomial on the top, polynomial on the bottom. To find their limits at infinity or negative infinity, and the nice thing is it's the same for rational functions going both directions, divide every term by the highest power of x and take the limit as x goes to infinity of f of x. Very fun. It's actually, this is going to be really nice, really slick, really easy. That also gets us the horizontal asymptote for the graph. Now, let's take a look at that example that I was just looking at. So f of x is equal to this mess. So what I want to do is I want to divide every term by the highest power of x. Well, in this case, the highest power is x squared. I have it on both the top and the bottom, and I'm just going to go through and do all that division. Perfectly legal. Remember, our limits, we have those limit laws, and we can divide things in the limit laws. So since this is not really changing the function, it's just making it look different, we can go ahead and divide everything by x squared. So I just went ahead and did that. I divided everything by x squared. I'll let you sort through it, but basically x squared divided by x squared is just 1, so I was left with the 2. Here, I'll be left with an x on the bottom, and 1 over x squared is 1 over x squared. Same thing on the bottom, the x squareds will cancel out when I divide. I'll be left with 1 on the bottom, and 8 over x squared. Now you're saying, okay, why did we make it do that? Why did we turn it into a mess? Well, because now we have something that's in a really nice format to take a limit. Okay, so I'm taking the limit of f of x as x goes to infinity, but I'm looking at this version of it. Because here's the nice thing, we know we have all those limit laws, and we know that anything over x, its limit is just 0. And in fact, we know that anything over x to a power, because of the limit laws, is also 0. So I can just go through and evaluate this. The limit as x goes to infinity of 2 is 2, and for 4 it's 4. But these other pieces all go to 0 because they have an x on the bottom. Which means we end up with a limit of 1/2, and we get a horizontal asymptote of y equals 1/2 as well. Pretty nice. I like the rational functions. They're really pretty slick. They work nice. So yeah, have fun with those. Let's keep going. All right, 2 examples here now using some limits involving infinity. There's all kinds of goofiness that's going to happen here. So buckle up and have fun when you do the homework. Let's find the limit as x goes to infinity of the sine of 1 over x. Oh boy. So to do this one, we actually are going to use a little bit of trickery to pull it off. I don't like the 1 over x, quite frankly. I know this goes to 0. Actually, I could probably do that, except we don't have a composition function for limits. Oh yeah, actually we did. Huh. So we could just go straight to 0. We know the limit on the inside is 0, and so the sine of that is 0. Hey, that would work. That wasn't my first thought, but that works because we had that composition function theorem. The other way, the way that I thought at first, was to say, hey, let t equal 1 over x. If you do that, this limit as x goes to infinity of the sine of 1 over x becomes the limit as t goes to 0 from the right. Okay, since we're going to positive infinity, that's going to be the same as t going to 0 from the right-hand side, from those positive values. And then we can put it in t for 1 over x. So now we just have a limit of sine, and we know that limit. It's just 0, right? Because we had the limits for trig functions, and those were no big deal. Last but not least, the limit as x goes to 0 from the left of e to the 1 over x. So this time, I'm going to use the same substitution that I just did. We'll let t be 1 over x. But now I get the limit as t goes to negative infinity. And that's because x was going to 0 from the left. So when we flip it, we're going to go to infinity. But because we're coming in from the left with those negative values, we're going to end up going to negative infinity. And this is just going to equal 0. We can show that. But basically, if t is less than 0, so e to the t is the same as 1 over e to the absolute value of t. And what happens to e to the t as t gets big? Well, it goes to infinity, and 1 over anything that goes to infinity is always just going to be a limit of 0. So there we go. Isn't that exciting? All right, let's see. I have more. Boy, do I have more. I have one more good example, and then we'll move on. All right, so here's a super fun example. We want to find the limit as x goes to infinity of x minus the square root of x squared plus 16. So why is this so much fun? Well, here's the thing. We could do the limit as x goes to infinity of x. That's just infinity. No big deal. And using the limit laws, we could get the same conclusion about the square root of x squared plus 16, right? As x gets super, super, super big, that whole thing is going to get really, really big. So we end up with infinity minus infinity if we try to just brute force this and say, hey, what does this equal? So we can't do that. Infinity minus infinity, it can be a lot of different things. Okay, in this case, I think we're going to end up getting 0, but that's not necessarily the case. Okay, very, very strangely, it all depends on how big are your infinities, or how quickly are you getting to them is maybe the better way to say it. And yeah, so let's see how we actually get 0 out of this one. So I have to first do a manipulation of my limit. I have this x minus the square root on the inside, and basically anytime you have something and then you have a square root with a minus or a plus sign, it's an indication that maybe multiplying by a conjugate is going to be a good plan. And so if we do that here, we multiply by the conjugate over itself, so x plus the square root over x plus the square root. And what happens then is a lot of stuff is going to get cleaned up. The bottom stays x plus the square root of x squared plus 16, but on the top we have x times x, which gives us x squared. And importantly, because of the conjugates, the x times the square root and the x times the minus square root cancel out and go away. So we're just left with x squared times, minus, and then the two square roots, when you multiply them together, just give you the mess on the inside. So feel free to go back and pick through that algebra just a little bit more, and feel free to show up and ask me questions about that if you need to. But now I can clean this up. I distribute the minus sign, the x squareds go away. I'm just left, should be a minus 16 on the top, though it really doesn't matter. I'm left with a minus 16 on the top. So all I have here is something over x plus, x. I got the square root of x squared plus 16, but guess what? This is just a sum of stuff that is, combinations of things involving 1 over x. So we know that this limit then has to be equal to 0 because this whole bottom is going to infinity. And so, yeah, you divide by infinity, you go to 0. All right, let's keep moving.